Hi guys, slight change for schedule. We were going to do look at the EAS pumps for the Range Rover and how to rebuild them, but quite a few people have asked for this. There's a lot of people, we're coming into winter and that, we're doing modifications on our vehicle, we're putting more lights on because more lights means better, of course. So we're going to look at relays today. Couple of bits of housekeeping to do first. As you know, we're still experimenting with our setup. When we go into this in a minute, I'm going to set something alight, so we're going to need to use the table protector underneath. I think that might cause some white balance issues, so bear with me if it does. Anyway, different types of relays here. We'll leave this one to last because that's actually the one we're most interested in. So why do we use them? Well, if we take this one for starters, because this is a good example, as you can see we've got 8 relays on this board. I may not go the right way. I will get better at this as time goes on, and I apologise for it. This board is designed for use with microcontrollers or digital electronics which have next to no current current switching ability. So if you tried to drive a large motor or a fan or anything that draws a lot of power directly from a microcontroller, it's going to end badly for the microcontroller. So what this does is allows you to drive such loads. We actually use these for switching low current mains from a 3-volt microcontroller. They're quick, they're simple. Yes, we can do it with MOSFETs, yes we can do it with triacs. This is just easier and there's no point reinventing the wheel. Those individual relays on there are much like this one. As you can see, it's a tiny little thing. This is good for 7 amps at 240 volts. AC and DC current are different. We're not going to go into that today. But again, small current in, large current out. Larger version, this one is rated at some ungodly current. That's a 10 amp relay. Doesn't sound a lot, and given what we're going to look at in a second, it really isn't. But they're different types to be aware of. Oh, they've all gone out of shot. Let's bring them back. There's very funny colour things happening here. Right, this one. This is a standard automotive relay. I'll just bring it up. There we go. So this one came from Halfords. There are other vendors, and I'd encourage you to use the other vendors because yeah, this shouldn't have cost £6, which is what it cost. Any of you that have worked on vehicles will be familiar with these. You've got your pins on the bottom for your connections, and these will plug into a fuse box, or with this little tab, they'd be bolted onto a bulkhead somewhere. These are what we're focusing on today because what we're mainly interested in also is in automotive things today. So what I will do now is we'll get things changed. We'll have a quick look at their colour balance as well, and we'll get set up and we'll show you why you need to use them, when you'd use them, and what happens if you don't. So, right, this shonky setup is our car. We've got our nice new fog lights that we've added here. These are 55 watt bulbs. 2 of them draw about 8 amps between the 2 of them. On the other end of these wires, we've got a fairly high current power supply, and we've got a nice little switch that we've put in the dash here as well. Now, obviously, the wires on this side are sized correctly. We're rated at 15 amps here. These are rated at 10 amps each, and this is rated at probably about 40 looking at it. This isn't. This little wire in here really is not up to the job, and this is a lot of wiring as well, because especially with headlights, those of you with older Land Rovers will have had the whole, you know, the headlights really aren't very good, and that's voltage drop on the wiring harness. All your battery wiring to your lights needs to be nice, big, chunky, heavy wiring. Yes, if you're drawing 4 amps, you can use 5 amp cable. Your voltage drop on that cable, though, will be significant and enough to affect the light output. It takes fractions of a volt for that to happen. So that's another reason you might want to use a relay. But the other thing is, this stuff isn't cheap. This stuff, the thin stuff, really is, and you can find it anywhere. So What's going to happen here then? So I have no idea how well this is going to work, but we're going to show what's going to happen to this switch. So let's just turn this on. This may or may not be visible. So what we have here, if it turns on, is a thermal camera. I don't know how visible this is going to be, assuming it even starts up. There we go. So there's our switch. You'll have to excuse the ghosting on here because this is set up slightly strange and I can't work out how to tell this where the camera lens is. So as you can see, we're sat at about 17 degrees now. I don't really want to touch this because I know this is all going to get red hot. So we've got 16 degrees there. We come down here, there's not a lot of heat there. What I am going to do is push these in here. Two reasons for doing that: one, they get hot; two, they'll blind the camera, and the third reason being they'll blind me as well. And we'll turn this on and we'll just watch what happens to this wiring and turn the switch on. Don't you just love it when a plan comes together? Something here is not. Now this may mean that we've already fired the switch. There we go, we're on. So if we go back to that switch, you can already see, and you have to excuse the interference pattern, but that is heated. That little wire there is getting absolutely red hot. In comparison, the high current wires feeding either side are nice and cool. And that will be my battery gone. But that's fine. You can see what I'm talking about here. I was hoping this was going to burst into flames, and it's probably going to start smoking while we're talking. Certainly that mug's going to start getting hot, and I need to watch that. Oh, lovely toasty. I should really find some way of balancing my coffee over there, shouldn't I? Right. But what we've already got here that's immediately obvious is the flexibility in this wire, and that really is quite hot. As you can see on the flare, the temperature on the switch is starting to go up as well. What will happen in fairly short order, we can actually see we've got heating taking place on the spade here as well. If this will melt. Now if we just kill the power a second, I have a piece of that thin wire. Oh, that's lovely and toasty. So this will eventually melt. If it doesn't melt and it works, you've got quite a voltage drop across this. And it will fail because as time goes on, these contacts will get dirty. They'll make less than perfect contact, and then they'll really start to heat. This will melt. So what then happens, if I can make this work, and just make sure the fire extinguisher is where I think it is. It is. So we'll just see if we can get that to hold like that. And there we go, we're back on again, and in fairly short order, I don't know if you can see that. Oh, that stinks. But what we'll do is we'll zoom down a bit, and hopefully it's not too obvious, but you'll see that things are getting very, very hot down there. Let's see if there is a way of making this slightly more obvious for you, because this isn't showing up as well as I hoped on the camera. So what's happened here is all the insulation on that has gone. It is smoking quite nicely. Let's see if the flare will give me any playtime. And there we go. That's actually the reason that moved, is the end of the wire has actually melted. If we pop that back on and we find that there, so that you can see is absolutely red hot. Let's just try and bring that back on for you. That's 140 degrees C. It is smoking. It's not red hot, but it's not far off. I should imagine if we put the right item against that, that would catch fairly quickly. Fortunately, I have just tidied up, but that you can see it's on and it's just melting away. Now, fun as that is, and I will actually make one now deliberately fail. I've got some even nastier wire than this. Fun as that may be, that's not going to be fun if it's in your dashboard. This is part of what causes some of the problems with the P38, is that some of the wiring is less than stellar. And again, right, we have our bit of paper. So, quick bit about vehicle wiring, very, very quick bit. We've got our battery terminals here. 1, 2. Got positive terminal there and negative terminal there. Our negative terminal is connected straight to the chassis of the car. So that's your earth straps, your engine earth straps and everything like that. We don't have to worry about running that as a rule. If you're working on a very old vehicle, I don't believe any of the Land Rovers do it, but certainly some of the much older vehicles do. Your positive will actually be connected to the chassis. If you connect a radio, any electronics device to one of those cars, the way you normally would, it's going to die. So what we did then is we then came in, we had our little bit of wire, which was pretending to be our switch. If we draw in the switch there, the reason I'm doing this will become apparent. And then that went off to 1, 2 bulbs, and then down to earth. So we got a couple of problems with this. The first thing is this battery here is capable of delivering hundreds and hundreds of amps. Even if we use this thick stuff, we're in trouble if we short anything out. So the first thing we would normally need to do would be to put a fuse in there. The fuse needs to be close to what you're running. So I think I worked that out as each one of those bulbs was 4.5 amps. So we've got 9 amps there that we're drawing, which is incidentally why the power supply was getting funny. And that 9 amps is appearing all the way there. And it also, if you take that link out that we put in for testing and go through that horrible little switch, it was actually going through there. Now I have a great feeling that that switch held up a lot better than I expect. Well, I know it held up better than I expected it to. That switch is rated 3 amps. So you're onto a loser there straight away. So the first thing you want to do is look at a fuse there. 10 amp is good. You're probably going to get failures on that, especially because when lamps are cold, they can draw a lot more current. It's more pronounced with loads like motors and things like that, but even lamps will briefly draw a lot more current. Possibly not enough to blow this, but over time, the fuse will weaken and then it will fail. So the next sensible one you've got automotive fuse wise is 15 amps. So we've got that there. So we've still got a problem because all of this wiring here is running all the way around our vehicle. So I'm looking out the window at my P38. I know where the battery is. I know where the headlights are. That actual run here need only be about 1 metre on my vehicle. We'll call it 2 because you've got to run across the top. Across the valence. So we can keep that nice and short and use nice heavy wire, which will help lessen the voltage drop here. So how does the relay help us? Right, well the first thing we do is we come from our battery, we come through our fuse, and I think we said we'd use a 15 amp there, and then we come to our relay. Now if you look on the top of the relay, and I'll draw this out because it will be easier for you to see if I draw this out. You have on the top of your relay that, and that. These are actually standard terminal numbers. So 86, 85, 87. A, 87 and 30. Now, depending on what kind of relay you get, got a little line in there, you won't have 87A. Most automotive relays you're going to use will not have terminal 87A. There's special uses for that terminal, which I might go into. And this relay here is rated 12 volts at 30 amps. Oh, 30, not 3. So loads of headroom. So what we need to do is, if we go back to our other one here, we've got our little switch here. So we need to replace that with the relay. And if you look here, we've got that same symbol. And if I draw on that there to show a 2-position switch, or 2-pole switch, yeah, 2-position switch, you can see we've got the same here. So what we need to do is we go in to terminal 30, like that. And then we want to come out when the relay is turned on. Now that's what the difference here is. So terminal 30 is our common, and it's shown connected to 87A, which means if I use this relay now and I buzz through between 87A and 30, which are these two, I'll get a connection. That's useful for changeover type circuits. But we're interested in 30 and 87, which are the two end ones here, and they're not currently connected. So we'll go here onto terminal 87. We then come out and we go into our lights like that, and then down to ground. Now doing this, you can put this relay using the tab, which I've now lost. You can mount that, you can buy proper sockets for these, and you can waterproof these and get these all nice. We're just going to use these here. However, this means that you can now put these behind the headlights. You could use 2 relays. You could put another relay here and drive just that one. In practice, for what we're driving here, it's not that critical. There's plenty of headroom on the relay in terms of current. You're not going to burn this out. So we then run our wire, one straight to there and one straight across the valence and over to the other light. Great, fine. How do we turn it on? Well, this is where this other part comes in. So I'll draw that in here. And one end of this is grounded to the rest. And you'll notice that on here and on the relay, we've got this little dashed line. This is a coil, and this is connected to this switch. We'll pull this apart in a bit and I'll show you how it goes together. But when you energise this coil, it pulls this switch in, closes the circuit, and your lights come on. So we run this one off here. What we need to do now is put a positive feed into here. Now you could take it from after your fuse, like that. You short those two with a switch. That turns the relay on, and that closes this switch and your lights come on. You could take that positive feed from somewhere else if you're down in the centre console, cigar lighter, something like that, but it does need to be fused. But what you're doing is shorting this and providing power to this. So I'll show you how this all works. We'll wire this up in a second. The other way that this is sometimes used is for dip dim. So if you've got a lower power set of lights, you could wire them in here. So now what's going to happen, and this uses this terminal 87A, is when the relay's not on, this lower power set of lights will be on. With some spotlights, you've got like the angel light effect. This would be ideal for that, because it means when your main lights aren't on, you still get your angel eyes, but when you turn the relay on, so we connect this again, the relay comes on, this switch closes, the power now flows through the main lights and the angel eyes are off. You can use this for all sorts, but the wonderful thing is what's going on here. So we're controlling 10 amps if we go with those lights. Yeah, I've rounded it up, I know. What's actually being drawn by this coil is hundreds of milliamps, and I could work this out, I could meter it, I can't be bothered, but that is a fraction of the amount of power needed to drive the lights, which means this switch is absolutely fine. A little push switch, even, and this is where a lot of people have asked, you can pull this positive supply off of another circuit. So if, for example, we draw another light in here, and this is one that's been specifically asked. This is the high beam feed from the P38's BECM. These relays in the BCM we know are fragile. They're not great. They do fail, and if you put another 10 amps on that relay, it is going to fail. So what we can do is, rather than going to other switches, bring that down onto here and join it to there. The amount that we're adding to this circuit is infinitesimal. The BCM is not going to notice it, but we're still switching the 10 amps up here through the relay. So obviously nothing down here changes. The other thing the BCM will freak out about is fault currents. It does it does monitor how much current is being drawn. If you draw no current because the bulbs failed, it will fault. If you draw over current, it will fault. That certainly applies to the MOSFET channels. It may apply to the relay channels, I'm not sure, but the P38 is capable of seeing a blown bulb and letting you know. So the odds are, yes, I think it's possibly monitoring, which means if you do damage by overloading this and it is a MOSFET channel, you're going to be in a whole world of hurt, because that is going to need to be changed and those parts are no longer available. So that mess gives you an idea of how it all works. So what we're going to do now is I'm going to pause for a second, clear this off. We're going to get some wire together and I'm actually going to wire this up. Right, we're back. So we've wired this up. It's not particularly clear, just because I've got to use what I've got to hand. But here's our relay. This is exactly how it's wired up. The terminals are the same. So we have our battery feed coming in here. That's this here. We don't have a fuse. We've got a power supply down here, so we're not overly worried about that. The power supply will cut out. So we go into our relay. We then leave by terminal 87, which is this here, and go out to our light bulbs in a jar. Terminal 86 is grounded, so that's this wire here, which goes round and joins the rest of the ground here. If you're doing this on a vehicle where the chassis is grounded, quite often this will come out and round and go on to the chassis with the bolt that holds the relay. This does not have to run back to the ground of the lights or the ground of the switch or directly to the battery. The chassis ground on a vehicle is plenty good enough for this kind of thing. It's only with extremely heavy loads, such as your starter, that you need to start thinking about separate earths. Or some of the Land Rovers, you've got aluminium bodies. There's some mileage in going back to common earth points on them, just because you can have problems with corrosion. Then we have this tiny little wire is what controls our light. Now, we've already tried controlling the light with a piece of wire like this, and you saw what happened. And you also saw that if we used individual strands, they just vaporized. So what we're going to do now, this will take a couple of attempts because this is right on the limit of my power supply. Lord knows how old this power supply is, but it's starting to complain a bit at this load. So if we just give that a positive power supply, which is coming via my meter, you can see the lights are on, and I can now quite happily play with them. And you'll notice that there's no sparking or anything going down here, and I can in fact pull out a single strand of wire. You can probably just see that just there. Now, when we did this earlier, that vaporized. The funny noises from the relay is my power supply, but you can see that's quite happy. That's drawing very little current. In fact, if you look at my meter, you can see that relay is drawing 130 milliamps. It is falling, and it will do as the relay heats, but that really is no current at all. That's well within the realms of what the BECM can handle. on the P38. It's well within the realms of what pretty much any switch you can think of can handle, and it's also well within the range of solid state electronics, so transistors and MOSFETs. You wouldn't switch this directly from a microcontroller. 130 milliamps, it's pushing your luck slightly on a microcontroller. But what you can hear there, that noise, is my power supply struggling to actually give out the voltage, the current that's required of it. But the other thing is, there are some other things you can do with this. So we could now use our changeover, which I've already covered. That 12 volts could come from somewhere else. Not so much on the P38A, because you've got some very funny electrics going on with the lighting switches, but you could take that off directly off the main beam switch on another vehicle. You could take that directly off of the main beam feed for the main beam light at the back of the light cluster on P38. And it really depends on what you're doing. There's so much you can do with this without having to resort to messing around with electronics. And by using the changeover function, you can do, it's a really good way of doing dipped in bulbs. I've used that before rewiring much older Range Rovers. And really, this is no current on here at all now. There's no risk here. There is one thing I do want to cover. We're unfortunately going to have to touch on some electronics here. I've tried to avoid doing this. I'm going to turn that off, because if I short that out, there's going to be smoke everywhere. I did promise you an explosion. I'll try and see what we can do about that. So, a little bit of boring stuff here. You don't necessarily need to know what I'm about to cover here, but it's worth knowing, because depending on where you get your relays from, you can come a cropper on this. Let's just pop this relay off. Now you can see quite clearly on the top of this relay, if I just focus down on this, I've piled too much stuff around my mouse. Come on, focus, focus, focus. Oh, wrong way. You can see you've got the terminals and everything on there, and the coil is quite clearly shown as just a box. I need to focus in again. There we go. So what we're going to focus on just briefly is the coils. So there's two ways we can drive this. So we've got a positive supply and we've got a negative supply. If they come in, we've got our switch, that comes out, and that drives the coil. Now that's the coil of the relay. That's exactly what it is. It's a coil of wire and then a solid iron core which you magnetise. If you're doing it electronically, and this is very rough and ready, you'd do the same. You'd come down into your core, out into a power transistor of some kind, and out there. You generally have a resistor in there, and that's what you're driving. So that's how you drive it from a micro. We've got a problem here. Not so much with the switch, but certainly with this. When you power this up, current flows through, it flows through in this direction, and you get a magnetic field forms in the transformer. Same with this. This is getting progressively worse, and I apologise for this. That's wonderful. Your relay's on, everything's happy, there's no problems in the world. Turn the relay off. This magnetic field has to go somewhere, and it collapses, causing what's called a back EMF. Now for our switch, that's not a problem, because we've now got a big spike of current trying to flow this way. The switch is open, there's an air gap. Not a problem. You may get some sparking or some progressive damage on the switch over time, but not enough to really worry about. This is a different kettle of fish, because transistors and MOSFETs are quite sensitive to this kind of thing. This sudden backwards current, which can be quite a considerable voltage, will destroy this. And you'll either have, best case scenario, you won't be able to turn the relay on anymore. Worst case scenario, that becomes a short circuit and you can't turn the relay off. So we need to do something about that. So what we do is quite a few relays will show on the top a diode, or you can fit one. And the idea is now that when your current is flowing normally, it flows up there and down through the coil. When it's backwards, caused by the back EMF, effectively it's now a closed loop. That current will circulate until it dissipates, and it won't do any damage here because it's preferably going to flow that way. There is resistance there, significantly more resistance than the diode presents, so effectively the current hangs a left and goes through the diode and goes round and round and round in circles until it's dissipated. It doesn't cause you any problems, and if you're doing most vehicle wiring, you're not going to need to worry about it. However, grab another bit of paper. Some diodes, and I don't actually have one here that has one, will show you on the top exactly the same as this one. So we've got our coil there shown like that, but they will actually show a diode across. Now the problem you've got is if you wire this up, you need to be aware of that, because for example, if you put the positive here and the negative here, your current is going to flow all the way there, round the diode, back out and through there. It isn't going to flow through the coil. One of two things is going to happen. If you put a fuse in here, the fuse is probably going to go. It's also quite likely the diode's going to go, which will render the protection useless, but they normally fail open circuit, so you'd still be able to use the relay, you just wouldn't have the protection. If you don't have a fuse, yeah, that's going, or your wiring's going. But if you wire it the correct way around, so the diode points in the direction of current flow, and yes, I know about conventional current, etc., then it will flow here through the coil and you're absolutely fine. But it means that that back EMF is going to flow that way when you de-energise it. It's just a gotcha. Right. What can we break? Bear with me. Let's see what we can do to demonstrate. So, quick one. What I'm going to do is, I know we said you could kill these diodes fairly easily and accidentally by putting a diode protected relay in the wrong way. So what I'm going to do is this little diode that I have here. Let me zoom right in. Focus. Bear with me. Am I making that better or worse? There we go. And this little diode here is indeed not going to go to market. This diode here is going somewhere completely different. So, just a quick one. I realise this actually isn't as focused as it could be. There we go. I want to be really careful with those because they're turned on. So, you've got your diode symbol here. This is just a quick bit about diodes. This really doesn't matter. So, positive flows to negative. You can't go the other way. And if you look at this diode, you've got a little cylinder with a stripe. That stripe is that. So the arrow points in the direction of travel. We're going to hit this diode with a massive overload. I have no idea what's going to happen. I do have safety glasses on because I suspect it's going to be spectacular and I may jump. Here we go. Just make sure that's all good. And bye-bye diode. Okay. That little diode is taking so much punishment at the moment. I'm quite frankly impressed. Yes, well, there we go. That didn't go quite according to plan. And we've left scuff marks on the thing. So, let's come back to this. I can take my glasses off now because I can't actually see anything through them. My God, everything vibrates around here. So, I've now taken the top off of that relay that we were working with so we can have a look inside. And as you can see, there's your coil. That really isn't focused that well. we get better? Oh, that's lovely. So we've got your coil in there. You grab the pointy stick. That's what you're powering up. And then once that's powered up, there is a magnetic core in there. You can see the back of the core there. We can possibly see the front of the core if I take that apart. And when you energise it, which if I turn this down to a slightly more sensible level, and we will energise that coil. Let's come across, remind myself of what terminal is where. You'll see it move, hopefully. Now if we look down here, you can see the contacts. They're quite hard to see at this angle, I suspect. But down here you have your central, so this here on the metal is your terminal 30. Then this contact here is your 87A, and you can see right now, if you look down there, it's pressing up against terminal 30, and 87 is this terminal here, which as you can see is not touching anything. Once you magnetise it, this plate, if I move it with my finger, moves, and you can see the contacts down there moving and changing over between the two. So there you go, that's a relay. I'm slightly disappointed that we haven't blown something up. There should be a good explosion of fire in every video like this, and unfortunately we've not managed it.